Hello, and welcome to a digital lecture for Salt Lake Community College. This lecture will be the third to cover Section 3.5 for Intro to Statistics, considering inference for a single proportion. This section will cover how we apply for a hypothesis test of one proportion, and also how to determine the required sample size when estimating a proportion. When conducting a hypothesis test, the same four general steps from hypotheses testing covered in Chapter 2 will apply, but here we will show how to specifically do so for proportions. First, we will frame the research question in terms of hypotheses. That means we're going to write the null and alternative hypotheses about the population proportion P. Second, we will collect appropriate data with an observational study or experiment. That means that we will verify that the data were collected appropriately by checking that they come from a random sample or a randomized experiment. We also want to ensure that observations are independent, which we check by looking at n being less than 0.05 times capital N. Recall that little n refers to the sample size, capital N refers to the population size. And lastly, we want to also make sure the sample size is large enough. We have two checks for that. We're going to see if n times p sub 0 is greater than or equal to 10, and also that n times 1 minus p sub 0 is also greater than or equal to 10. Third, we will analyze the data. If the conditions hold, we will construct the standard error, again using p sub 0, and show the p-value in a drawing. Fourth and last, we will form a conclusion. We will use the p-value that we find to evaluate the hypotheses. If we take the formula for confidence intervals covered in the previous lecture and solve for the value of n in the margin of error algebraically, we find the sample size calculation formula for estimating a single proportion. This is shown here as little n is greater than or equal to z star squared times p times 1 minus p divided by the margin of error squared. Here, z star corresponds to the confidence level for the interval. For example, if we were doing a 95% level of confidence, we would typically be using 1.96 for z star. The p there is an estimate of the proportion from a similar survey, and me, as I stated, is the desired margin of error. If no estimate of the proportion is available, the formula changes a little bit and becomes little n is greater than or equal to z star squared times 0.5 times 1 minus 0.5 divided by the margin of error squared. Or, since we are now substituting 0.5 into where p is, we can calculate the top algebraically. 0.5 times 1 minus 0.5 gives us 0.25. Notice that in such observations or calculations, we will always round up for the sample size. Rounding down would result in a value for n that is below the minimum necessary sample size. The primary reason for that is the symbol that is used between the two sides of this inequality. We have a greater than or equal to symbol. If, for example, we solve the right side of this equation and we get a statement that says n needs to be greater than or equal to 72.1, and we were to instead try to choose a sample size of 72, well, then this statement is not true. The sample size we chose of 72 is not greater than or equal to the necessary 72.1. This is why we're going to always need to round up. We're going to need a whole number anyway, so when we calculate that right side for 72.1, we're going to take that and instead make a statement that says n needs to be greater than or equal to 73. Because any value of 73 or higher is inherently larger than 72.1. Now, we talked before as well about what affects the width of a calculated confidence interval. And in turn, we also have some things to consider for the required sample size. If all else remains constant, changing a component of the sample size calculation will have the following results. If we increase the confidence level, that will increase the minimum sample size. A value of p hat close to 0.5 will require a larger minimum sample size than a value of p hat close to 0 or 1. And also, a larger desired margin of error will decrease the minimum sample size. Now, let's look at an example of dealing with a hypothesis test. Some people claim that they can tell the difference between a diet soda and a regular soda in the first sip. A researcher wanting to test this claim randomly sampled 80 such people. He then filled 80 plain white cups with soda, half diet and half regular, through random assignment, and asked each person to take one sip from their cup and identify the soda as diet or regular. 53 participants correctly identified the soda. Do these data provide strong evidence that more than 50% of people who claim that they can tell the difference between diet and regular soda in one sip actually can? We will use a 5% level of significance. First, when we state our hypotheses, we note that the goal of the study, the second to last sentence here, was that more than 50% of people who claim that they can tell the difference. That's what we're trying to show. Therefore, that 50% will be our p sub 0 value. It will define our null hypothesis as p is equal to 0.50, indicating that there is no difference. Whereas the alternative hypothesis will be that more than 50% of people can claim the difference. When we check the requirements, we note that the statement did say that we randomly selected 80 people, so we do have randomness. For the sample size being less than 5% of the population size, we can claim that since we are showing that we are just using 80 people, which is likely less than 5% of all people, but if you want to calculate it out more specifically, we can find that 80 is less than 0.05 times capital N, divide 0.05 over, and show that 1600 has to be a lower limit for the population size, and there are many more people than that exist. Lastly, to ensure our sample size is large enough, we have to show NP is greater than 10, as well as N times 1 minus P is greater than 10, which for both of these instances, both P and 1 minus P are going to be 0.5, which means 80 times 0.5 and 80 times 1 minus 0.5, both of which calculate to be 40 and are greater than 10. If the null hypothesis is true, what does the sampling distribution look like? The mean should be defined as p sub 0, the value in our null hypothesis of 0.5. The standard error is defined as the square root of p times 1 minus p divided by n. So we have the square root of 0.5 times 1 minus 0.5 divided by 80, our sample size, which results in a value of about 0.0559. If we then try to make our curve and show what we're looking for, we have a curve with a center of 0.5, and p hat, our sample proportion, is likely above that. And then what we would likely try to find here is the value of the p-value, which is the probability of seeing something as extreme or more extreme than our sample proportion. In terms of what values would be surprising, well, that depends on the p-value. Values where the associated p-value is less than the 5% significance level would be surprising for us. We then compute our test statistic and our p-value. The test statistic is defined as p hat minus p sub 0 divided by the square root of p0 times 1 minus p0 divided by n. We have a calculation that looks like this. 53 over 80 minus 0.5 divided by our standard error we calculated earlier of 0.0559. And this evaluates to a z-score of about 2.91 for our test statistic, almost 3 standard deviations away. To determine the p-value, we can find that by either using the normal probability table in the appendix of your textbook, or we can do so with GeoGebra as demonstrated on the right side here. I will leave that to the GeoGebra video. However, as shown here on the right side, the test statistic calculated is 2.9069, the same that we got from our hand calculation, and a p-value of 0.0018. So that is our p-value above the sample proportion of 53 out of 80. With the p-value calculated, we can draw our conclusions, keeping in mind that the p-value is less than alpha, the significance level of 0.05. Because it is less than 0.05, we will reject the null hypothesis and claim that there is sufficient evidence to conclude that more than 50% of people can tell the difference. As for what the p-value means, we would say that about 2 in every 1,000 samples. I'm getting that value from taking our p-value 0.0018, multiplying that by 1,000 to get about 2. So about 2 in every 1,000 samples will give a sample proportion as high or higher than the one obtained if people cannot tell the difference between diet and regular. One of the examples on the next page will cover more of how to deal with this in GeoGebra, which again I will leave to the GeoGebra lecture. However, we will also do the example after that. A school administrator is concerned about the amount of credit card debt that college students have. She wishes to conduct a poll to estimate the percentage of full-time students who have credit card debt of $2,000 or more. What sample size should be obtained if she wishes to estimate to be within 2.5 percentage points with a 99% confidence if the pilot study indicates that the percentage is 34%? First, what we should do is identify the values that are presented. Since it says the pilot study indicates the percentage is 34%, that is going to be our prior estimate, P. We also have our margin of error is 2.5 percentage points. Keep in mind that we need to represent that as a proportion, 0.025. And because we're making a 99% confidence level, that is going to dictate the value for Z star. For a 99% confidence level, that means Z star is 2.58. With all that in place, we can plug that into our formula to find the sample size necessary. We would plug in all three of those values there and get 2.58 squared times 0.34 times 1 minus 0.34 divided by 0.025 squared, which results in a value of about 2,389.9. Keep in mind that this says n is greater than or equal to that value, which means our final conclusion for this is that we need at least 2,390 participants. Note that even if this value was 2,389.1, I would still round this up to 2,390. If instead we have no prior estimates used, then the value for the prior estimate we will use is 0.5, with the same margin of error and z-score. If we plug that into our formula for the required sample size, we will find we have 2.58 squared times 0.5 times 1 minus 0.5 divided by 0.025 squared, or just 0.25 in the numerator, which results in a value of 2,662.56. Like before, we are going to round that up because we are looking at n is greater than or equal to that value, and therefore our results will be that we need at least 2,663 participants. If you have any further questions, be sure to review the example videos or ask your instructor.